My dear friends, welcome to Rajshekhar classes on Applied Data Science with Python. This is lecture number 517. In this lecture, we will try to understand modeling. Now, we will train a simple model. The most important part of this case study is featureization. Modeling is a straightforward thing because we have seen so many other case studies where we are modeled. So instead of training of many models, my gut feeling shows that a fairly non-linear model might works. Well, we are loading data. Just say this one. We are loading data. We have seen code snippet for this one snippet computed for every source and destination vertices. We have computed all of these features. Anyway, I will keep this IPython notebook in this particular lecture description section as well as in comment section. Just go through that IPython notebook. We have computed all these features. We just loading all of this data. So rest of the code snippet here. Whenever you see test, what does it mean? It's a test means what? Test, it means cross validate, isn't it? It's the meaning of test here. In this particular context, you have test means what? It's a cross validate because you are doing hyperparameter tuning. We have trained data and also cross validate data. As I told you, I will keep this particular IPython notebook. Just go through it. So here test basically means it's cross validation. So we will do hyperparameter tuning on train and test data. We are using the random forest classifier, isn't it? What is this random forest classifier? Just say random forest classifier, because we know that random forest classifier typically tends to work well when you have reasonable number of features, not too many features, and when we want to take care of non-linearities automatically, isn't it? I will repeat this one as this point is very important. Here in this particular case here, test basically means it's cross validation. So we will do hyperparameter tuning on train and test data. We are using the random forest classifier because we know that random forest classifier typically tends to work well when you have reasonable number of features, not too many features, and when we want to take care of non-linearities automatically. I don't have to do further non-linear transformations and interaction feature stuff like that, isn't it? While we jump directly into random forest, we recommend you to try out other models also, since this is the first cut solution that we are providing. We directly jump into the random forest. Of course, GBDT linear models, SVMs might work reasonably well on this data set. There are two hyperparameters. There are two hyperparameters that we have for random forest. One is that number of estimators, isn't it? Number of estimators. The other one is the depth. This is standard hyperparameter tuning on number of estimators are the base models. There are 10 base models. There may be 50 base models, 100, 250, 450, like this. And we found the best number of the best number of base learners is 115. That is 115 based on both train and cross validate score. Wherever test is written, it means, as I told you, cross validation, isn't it? Cross validation score here. So we also plotted, see, remember, we are using F1 score as a metric. We are also plot how the score changes between your train data and your cross validate or test data as a number of estimators. Change as how your cross validate or test data as number of estimators change, isn't it? And your depth I am taking on x-axis and score on your y-axis. Just see here you are taking using we are using F1 score as a metric. We are also plot how this score changes between your trained data and your cross validation or test data as a number of estimators change. Having said that, we also we also have hyperparameters tuning on the depth of the base learners, isn't it? With the depth 3, 9, 11, with the different depths. Just say this is with the different depths we are doing. With some hyperparameter tuning, we got the score here as a depth. As depth changes, as depth is 0, just see here depth you are taking on x-axis. As depth changes, so beyond depth of 0, depth of 20, so beyond a point the depth does not improve the model much. Similarly, if you notice here, beyond certain number of estimators, just see beyond certain number of estimators the model does not improve significantly. So standard hyperparameter tuning, isn't it? Let's simply do, it's a standard hyperparameter tuning which we discussed many times, isn't it? Let's simply do randomized there is some randomized search. We found some reasonably good values for number of base learners and depth, isn't it? We got reasonably good values for number of base learners as well as depth. If you notice, we typically tend to get about F1 score on the trained data as what is your F1 score on trained data, that is 0.965 on the cross validate data with 0.924, fairly close, and these are not far away. And since these two values are close, train F1 score value and test F1 score value, we know that we are not overfitting to the model. Here test basically means cross validation. Let's not forget that. Here our training F1 score and cross validate F1 score are close to each other. We need not worry about overfitting. We also plotted the confusion matrix. Just I request all of you, if someone has, we already recorded a lecture on confusion matrix. Just before understanding this lecture, just go through that confusion matrix lecture. We also plotted the confusion matrix to understand what's happening on the trained data itself. You have confusion matrix for trained data itself. We have precision and recall matrices. I have precision matrix and recall matrices. The precision for class 0 is, what is the precision plus class 0? 0.954. If this particular slide is not that visible, I kindly request all of you to go through the IPython notebook, which I will keep in the description section and comment section of this particular video. Just say the precision for class 0 is 0.954 and the precision for class 1 is 0.978, isn't it? Very high values. One thing that is slightly off is, just see the values here, which values, this these values 0.046, this value, if you observe this one 0.046, this is 0.022. This value is smaller than this value, isn't it? In similar manner, 0.021 is smaller than 0.048. These values are smaller. Just observe those values. The recalls are also pretty healthy. The other thing that you notice is this is training data. Just say you have this one as training confusion matrix. This is test confusion matrix, isn't it? If you notice that there is a significant drop here, just see here you have significant drop. Where you have significant drop here, if you observe, this is 0.954, isn't it? Here you have 0.891. Yes. Precision matrix, I can say, what is this matrix? This matrix is precision matrix. Just observe, this is precision matrix. This is also precision matrix. Of course, this is precision matrix for training and this one is testing, isn't it? There is a significant drop where these two values are looks, just see these two values, this value and this value look similar. Which two values? Just see these two values are look similar, isn't it? Very similar, which means in the training data, whatever is the precision that we get for class 0 is not carrying forward to the test data or cross validate data. Just observe recall matrix also. If you observe recall matrix, there is a significant drop here. Here you have 0.952. Just observe this one. Here you have 0.952, here 0.880. So the recall for class 1 is dropping and the precision for the class 0 is dropping. That is important. Recall for class 1 is dropping and the precision for class 0 is dropping. So what this suggests that we could add more features to be able to more precisely determine, isn't it? You can add few more features. If something is class 0 or not, to decide you can add few more features. Basically, given a pair of vertices ui comma uj, let me say ui is a vertex, uj is a vertex. Given a pair of vertices ui comma uj, if we can come up with more featureizations, that can help us more precise in determining the determining 0 class, and it's doing fairly well on trained data, and it's not doing on cross-validate data. Similarly, the recall also have issues with class 1. Again, this could be because of multiple reasons. Remember, we also had cold start problem. Just try to recall, we discussed about cold start problem. In previous lectures, we discussed cold start problem, wherein we have some vertices in the test or cross-validate that we did not have in the original training data. So the reason I am calling cross-validate our test is because we are using this data for cross-validation here, not specifically for testing, because we have only broken our data into dtrain and dtest, and dtest we are using this dtest the dtest data we are using for cross validation. The actual testing will happen when we deploy the model and test in the real world. Of course, you could have broken of this data into 3 pieces that will have its own complexity. We plotted the ROC curve. Just say this ROC curve for the cross validate or test data, and most important part is feature importance. It's always fun. Look at this. Just say this is feature importance. So follows back is the most important feature, which means UI is following UJ. Then there is a very high chance that UJ follows UI, isn't it? So follows back is one of the most important feature, followed by weight. There is something like weight cosine features, shortest path. Again, weight feature is important. If you look at the weight importance, if you look at the feature importance, SVDs are not that important. Just I will show you this IPython notebook once before concluding this particular lecture. Just see this one. This is my IPython notebook. Just give me 1 minute time. Yes, maybe yes, 1 minute. Yes, this one. Just see, this is my IPython notebook, where we can see follows back, weight and score F1, cosine followers. Even if you want to make it just little bit big, if you see what's happening here, you have here SVDs. What it says, except the last 6 features, they are related SVDs. Except the last 6 features, rest of them has some value. Just see, all these are having some values. You can see the feature importance. This from this particular graph. Follows back, weight and score F1, cosine followers, shortest path, intermediate followers, weight and score F3, weight and score F1, number of followers, weight and score F2, Jaccard followers. Just see this one. Just go through this IPython notebook so that you will get clear understanding. Weight out to inter followers, cosine followers, so same, isn't it? Page rank, like that. There are many features. Except the last 6 features, rest of them has some values and some contribution towards improving the model performance. The most important thing in this particular case study is obviously the model. The most important in this case study is featureization and feature engineering. Just go through this lecture. With this particular lecture, I am concluding this particular case study. As I told you, I will keep this IPython notebook. Just go through that IPython notebook. Just study this particular case study, which has got so much of importance in data science and machine learning. Thank you very much.